Proctor. Mike is from Cambridge, more or less his whole life. He was an undergraduate there. He went to graduate school. Well, actually, between undergraduate and graduate school, he was a Kennedy Fellow in the US at MIT, and then did a PhD under Dennis Keith Moffat. Came to the US, did a postdoc at MIT as well under Willem Malkus, and then has been a professor at Cambridge University ever since. I think he'll probably say that way. Also, he's a fellow of the Royal Society at some point in time. So he's going to be discussing all kinds of things about magnetic fields and dynamo action.
Thank you, Jeff. Thank you very much. So this is not a microphone so that you can hear me, right? So I have to speak up. It's only for the audio.
Yeah.
Yeah, I'm sorry I didn't put my makeup on because nobody told me it was going to be filmed. So this is, I can talk about some work that I've been doing over the last few years with David Hughes, who's at Leeds. And I'm going to, because it's material I suspect isn't familiar to most of you, most of it is a review, will take up some of the time. The very small bit that I'm responsible for will appear in the middle somewhere. But first I want to concentrate on this logo. This is a joke, it's not mathematics. You see this very modern logo of the University of Leeds, with a very traditional and excellent logo for the University of Cambridge. And if you, Leeds has progressed more than Cambridge, and this is how it's progressed. They started off with a perfectly sensible Shear, white rose for Yorkshire, etc., etc. And then they wanted to become more modern. So here's this logo of the University Tower at Leeds, central, you notice, in the picture. And then they spent a lot more money, a more edgy logo, and just moved that tower just across to one side. Isn't that a good use of public money? I think so. Enough of the University of Leeds.
If it helps, you can also do that to
Okay. That's good. Nice knot. So I want to talk about dynamos. Well, many of you know what a dynamo is in the astrophysical context. It's a mechanism by which kinetic energy is, power is transformed into magnetic energy through electromagnetic induction. And years ago, it was thought to be rather difficult to do this. The reason that people thought it was difficult was because many flows that could be looked at analytically or with tiny computers were very smooth and simple, and there was a lot of argument about whether if a flow was simple enough to understand, it was too simple to act as a dynamo. But now we know better, and in fact we know that it's quite easy to produce magnetic fields by a variety of mechanisms through induction when, as long as the flow is complicated enough and vigorous enough. Because there's always the effect of magnetic diffusion to make currents and fields decay. You have to move the fluid fast enough, or shear the fluid fast enough to get magnetic field to grow. Having decided that you can have growing fields, you can then make a useful distinction between two types of dynamo action. So the first case, so-called small-scale dynamo or fluctuation dynamo, this is a mechanism which essentially can be understood as simple stretching of magnetic field lines through the Faraday mechanism. So you ignore diffusion to the first approximation. Oh, that is good. That's it. Sorry. Was it okay? No? How do I do that?
Screen there.
What happened?
I don't think it's just okay. You're back.
Okay. Thank you. I just pulled it out. It doesn't screw it. Sorry. If you don't have any diffusion and you have a complex flow with lots of stretching at nearby points in the fluid diverge exponentially, it's very easy to show that you can get initial growth of magnetic energy. What you can't do without diffusion is to enhance the amount of flux in a closed conductor. So a sphere conductor, for example, surrounded by insulator, you can, without diffusion, you can increase the magnetic energy, but you can't increase the flux or the dipole moment. You need diffusion for that. But if the flow is sufficiently vigorous, then the stretching mechanism dominates diffusion, and you can eventually get growing fields and growing dipole moments, which fulfill the requirements of the dynamo. So there are several properties here. There's stretching, which enhances the energy, but there's also cancellation, because the surfaces of the magnetic field have to be folded on each other in a finite domain, and so obviously the directed field lines can be brought together, and they tend to diffuse rapidly. But as long as the field is of the right type, the stretching process dominates this cancellation process due to folding and diffusion, and you can get exponential growth. Now there's nothing in here that says anything about rotation, chirality, anything like that. So this is simply pulling and squeezing to increase the magnetic energy. It doesn't have to be chiral, it doesn't have to be rotation in your system, it doesn't have to be anything. There's a small scale effect, and the resulting magnetic fields have a scale comparable to the scale of the velocity field. But there is another kind of possible dynamo action where, even for very weak flows, you can produce magnetic fields on very large scales. And the way you do that is to have a separation of scales. This may not be very realistic, but small scale flow can interact with small scale induced magnetic fields. So you have a large scale magnetic field, essentially constant. Then you have a small scale flow that produces small scale magnetic field through the induction process. And the EMF, electromotive force, comes from the interaction of a small-scale flow with a small-scale field. And that large-scale EMF can drive changes to the large-scale magnetic field. Now, stated baldly, there's nothing about rotation there, but it turns out that in the usual approximation that are used to find large-scale dynamos, the essential ingredient is chirality. You have to have broken mirror symmetry in the statistics of your flow. And so it's a very different process from this. But this will work even when the diffusion dominates on the small scale. In fact, there's a rigorous theory produced in the limit that the magnetic Reynolds number, which measures the strength of diffusion, inverse strength, the magnetic Reynolds number is very small on the small scale, so diffusion is very important, but very large on the large scale, so diffusion is unimportant on the large scale. So there is an interesting limit there, which you can do analytically. So this really does work. Any flow with chirality, essentially, a three-dimensional flow with chirality, can act as a dynamo on sufficiently large scales, if you have those large scales to play. So it's an interesting question whether you can find these large-scale flows, these large-scale dynamos, in nature, rather than in simple theoretical constructs. And in fact, although you could do this rigorous theory, it doesn't apply, of course, to many astrophysical bodies because the magnetic Reynolds number, the importance of flow relative to diffusion, flow is very important relative to diffusion, even on the tiniest scales. And so these theoretical ideas don't work very well.
You've conspicuously not mentioned differential rotation.
No, that is also useful but not essential. So you can have no mean flow at all and still have dynamo action on large scales due to small-scale parallel flows. You can also have differential rotation. That by itself cannot produce a dynamo. For technical reasons, there's no radial component. So you do need both, but you can do, well, you don't need both. You need the small-scale effect, but you can do without a differential rotation if you really want to.
Well, I understand the principle, just in practice
There's always differential rotation.
Not an essential ingredient.
It's a ubiquitous ingredient. Being pedantic here, I'd say it's not an essential ingredient. Yeah?
When in math, in your simulations, you have a sense of the relative importance of differential rotation.
Well, I think in practice, most of the
Yes.
cases are the ones where we don't get that the stretching, but central rotation is a significant place.
Absolutely.
But yeah, there are these other pathological alpha squared cases where you don't have to have it, but in practice, yeah.
In practice, there is always differential rotation in rotating systems, of course, and that is an important thing, but it doesn't, from a technical point of view, not necessary for this small-scale process to work. I agree with you about its importance. Okay, so lots of people have looked at, okay, so we have shear now. So I really want to talk about the effects of shear on this process. So here we have differential rotation. So we know that there's a large-scale component to these global flows, differential component to global flows in astrophysical bodies. But I'm talking about something a bit different, that if you you take turbulence and you shear it, does this make any difference to its dynamo properties? It's a local dynamo property system. And can you produce, well, if you have a helical flow, then the shear tends to make the velocity spectra perfectly perpendicular to the direction of shear. So that in itself, that's good for dynamo action. Not that it's not good for dynamo action, rather. It's not a good thing. But of course, the existence of shear flows allows this alpha omega dynamo process. So there's a bit of a trade-off. You can alter the turbulence, so it doesn't work very well from the alpha effect point of view, but on the other hand, you have this global process involving differential rotation, which is a very powerful way of producing strong fields in the toroidal direction. So, if you have motions that are initially non-helical, and then you add shear, it turns out, from very clever calculations and very strange limits, you can show that an alpha effect, which is a mean EMF in the direction of the field, such as we want to construct, can occur even if the shear itself is non-helical. There's also a possibility, even if you don't have mean helicity, chirality, but you have fluctuations in the chirality, which is typical of turbulence, even in a non-rotating system. If you have fluctuations in the turbulence, so we have a fluctuating alpha effect, then you can, and you also have rotation, then you find that there's another effect, not quite the same as the alpha effect, but which also can help with dynamo action. So there are lots of possibilities in the presence of shear. And the interaction of shear with fluctuating EMFs, as I've said, can be shown to enhance dynamo action. So there's an initial method by Vishniak and Brandenburg, and I and the students to take it a bit further. And Hughes et al., which I'm going to discuss in a minute, have shown numerically how the action of a simple shear on non-helical turbulence can lead to large-scale dynamo action. Which is very interesting. So we have to ask some questions here. What is going on? Well, how does the shear interact with the small-scale flow? You have a flow which is not a large-scale dynamo, not a dynamo of any kind. If you add shear, you can make it into a dynamo, as I'll show. So are these dynamos small-scale and modulated by the shear, or are they really mean field dynamos where there's some new effect on a large scale produced by the existence of the shear? In this first case, the dynamo is more or less what it was before, just some small scale dynamo with large scale components because the shear flow itself exists on a larger scale. So it's not quite clear. Anyway, I'm going to in a minute try and answer this question by looking at convection in the fluid layer. But first I want to talk about this paper by Hughes et al., or two papers actually, one with rotation and one without. And they looked at a simple shear, a linear shear, with a computational box on an initially non-helical forced turbulence. So it's not really turbulence. Forced flow, velocity forced by a non-helical forcing function, and a non-rotating frame in the first paper. In fact, the addition of rotation doesn't do a great deal to this one. So shear is imposed in the y direction, and it's linear in x. The box, it's a cubical box they do their computations in. The box is very tall compared to the scales of the turbulence, and indeed compared to the other two sides. So it's like a great tall high-rise tower in the z direction, and the size of the box in the x and y directions, the other two directions, is not so different from the scales of the small-scale motion that exists inside. When you have various boundary conditions which are periodic in z, periodic in y, and in the x direction you have the so-called shearing box condition, which incorporates the effect we see of shear. So the results are quite interesting. What they find is you add shear to this system, leaving everything else the same, it enhances field growth. Eventually, a large enough S, a velocity field which is not a dynamo in this long box becomes a dynamo and the field starts to grow. This is the growth rate as a function of the shear. Various box sizes. And if the box is long enough, it doesn't matter how long the box is, so it's independent of the box size, as long as it's big enough. If the box is too small, you can't see these effects because they have to be very large scale. And there seems to be some linear dependence of the growth rate on the shear, although not for small shears. It's a pity that this plot was not done linear, because if you want to prove a linear gradient, you don't need to take a logarithm, and this sort of inhibits one seeing the fluctuations are sort of compressed by the logarithmic scale there. So it's not, if you look at the numbers, they're not quite as good as they look, but there is this broad trend, linear growth, of the growth rate of the shear. Of course, the sign of the shear, the sign GM of the shear, is irrelevant to this problem. We change the sign of the shear. It's the same problem. So whatever the growth rate is, it's an even function of the shear. If this goes down to below 0, which you can't see in a log plot, then there must be another one on the other side, which is just the same. Or else this may be, analytically go like the square of the shear, small shear. But up here it looks like it's linear in the shear. And this here is the characteristic scale of the magnetic field in the z direction as you decrease the shear. So this is the shear parameter, the magnitude of the shear, is s to the minus a half. So going this way, the shear diminishes. And this way, these dots represent the vertical, a typical vertical scale of the magnetic field that results. And you can see that as the shear gets smaller, vertical scale, look at this right, it's roughly up, vertical scale decreases. Not understood. But that's not really understood. This needs some modeling effects. But it is very interesting, this result, because it shows that you can get long wavelength magnetic fields, much longer than any other scale in the system, when you impose a very simple shear on a small scale flow, which is homogeneous in the z direction. But we shall have to see. Seems to be a line missing here, I'm sorry. This is not a dynamo, but S equals naught, is what it's supposed to say. When there's no shear, it's not a dynamo. So the shear is responsible for dynamo action, and there's this nice linear dynamics. Okay, so we wanted to look at the effects of shear on a convection problem, which we understood better, perhaps a bit closer to astrophysical ideas. And this has been looked at a lot without any shear, so I'll just describe this problem briefly. So here we have a layer of fluid with stress-free boundaries, which is easy to deal with, rotating about the vertical axis. Gravity is in the z direction. Heated from below, so it's hotter here than it is here. And we're in a rotating frame, and I've written down the non-dimensional equations here for the motion of fluid. It's assumed to be incompressible. It's very simple. Compressibility adds new wrinkles, but doesn't, in my view, really alter the nature of the problem. It's much easier to compute pure equations. So the Taylor number is a measure of the square of the angular velocity. So it's the Coriolis force here, the inertial term. There's a term, these are linearized equations, I should say. One should really have nonlinear equations. There are nonlinear terms missing. I do apologize. This one is correct. There should be a u dot grad u term in here, and a u dot grad theta term in here, which I'm going to do like that. So theta is the perturbation temperature, driven by the vertical velocity, acting on the initial gradient of the temperature, which is linear in z. And then you have buoyancy force, viscosity, and the Lorentz forces acting here, and you have the induction equation for the magnetic field. And zeta is like the ratio of diffusion coefficients between magnetic diffusion and the thermal diffusion. That is flows and compressors. This is a very standard system, except that I've left out some important terms, which has been investigated by a lot of people. The convection itself is easily computed without any magnetic field. I'll do that in a minute. There's some pictures here, but I'll come to those. So what do we know about convective dynamos? I've shown you the model. The fluid is rotating, and it turns out that such convection, when sufficiently vigorous, acts as an efficient small-scale dynamo. So you readily get dynamo action. Even when it's not rotating, you can get dynamo action. And the effects of rotation on the nature of the dynamo are very small. So the mechanism turns out to be stretching. So it's a small-scale dynamo. Rotating helps a bit, but not very much. Too much rotation doesn't help at all because of the fixed temperature difference. You rotate the system fast enough, you impede convection. And in fact, there isn't sufficient vigorous convection to drive the dynamo, or sometimes even convection will disappear if it's too rapid rotation, given temperature contract. So convection, the rotation doesn't really help very much in these dynamos. It's of marginal importance. Stretching is the answer, and the dynamo is a small scale with no obvious mean large scale component. As I say, even in the presence of rotation, so with rotation you now have chirality. So the helicity of the flow, the correlation between vorticity and velocity, it's odd about the mid-plane, but it's definitely non-zero almost everywhere. And this is precisely the situation where we might expect mean field dynamos to appear. There are lots of simple analytical models which show how such a mean field dynamo can occur due to cellular motion of a simple sort with this chirality, which is odd about the Big Bang. So, you might think then, when you did your convection, which is very disordered, but very vigorous, that you would get a similar dynamo of mean field type, even when perhaps there wasn't a small scale dynamo. But no, as you'll see, the EMF that's produced, which would drive such a mean field dynamo, is very small. And there's no evidence of any significant mean field. There's a bit of a surprise, because we hope that convective dynamos, in the sun, for example, are responsible for the mean fields that we see. We don't understand at this moment how this really works. And as I said here, there are circumstances when the convective flow can act as a mean field dynamo. But these are in special parameter ranges for rapid rotation, very ordered convection, simple cellular flows, some things that theoreticians like, and the only things one can do in these remote times invented to consider. Well, it turns out that for large enough domains, and David Hughes and Cattaneo have investigated this in detail, for large enough domains, any correlation that might lead to significant mean EMFs is very weak, except possibly the very large rotation rates. You haven't done a complete survey. So, although you have these events which twist the fluid and produce an EMF of the right sort, when the flow is very vigorous, the amount of twist is very variable, and the correlation between different parts of the fluid layer is very weak. And so the net effect is very small, as we will see.
Quick question before we go on. With this considers the effects of convection, what's the present understanding of the extent to which mean field builds up on the scale of an individual convective cell? So,
you mean, that's what I would call a small scale dynamo.
Exactly.
Yes, okay. So
is it really convincingly demonstrated that such limited mean field, and so an individual's pressure scale height is generated?
Well, this is an incompressible calculation. In compressible flows, it's harder to, we've done some simulations with fully compressible flows. You can produce small-scale dynamos. There are problems in the dynamic regime because the fields are very filamentary, as you'll see, and they lead to evacuation locally, which is a problem. But in the kinematic case, if you want, can a tiny field grow? Yes, is the answer. It's a similar sort of process. Okay, so here's some examples. All of them are moving. I didn't realize that was moving. That's amazing. Okay, so this is Cattaneo's work on convective dynamos without rotation. There's no rotation here. If you choose the Rayleigh number, which is the measure of the temperature difference, make it large enough, you get dynamo action. And this is a small scale type. There's no large scale mean field, as you can see. So these, what you're seeing here, this is also so what you're seeing here, thank you, is like if you were looking at a magnetogram of the sun. So the black and the white, the two polarities of magnetic field. The magnetic field boundary conditions on this simulation are that the field is vertical, top and bottom. You're seeing that the total field coming out of the convective box, top and bottom. And you can see it's all tight, very filamentary between cells. In the interior, on the other hand, I'm going to make this actually go again. So in the interior, it's much more spaceful. It's the same calculation as this, just rendering now of magnetic energy rather than looking at individual field lines. Or maybe this is temperature, I can't remember what this is, but it's a measure of the energy of the magnetic field. And you can see that it has a scale comparable with the cells in motion. This is the magnetic field in the middle of the box, which relates to this. So it's much more filamentary at the top than it is in the middle. And but such structure as there is less than or equal to the cellular structure of the convection. About 100 convection cells in the box at any time. So this is definitely a small scale dynamo. If you looked at the spectrum, you would see no large scale term in it. So you take horizontal average is almost nothing in horizontal average of the horizontal field. So, there is no net flux. You have to be careful what you measure. But if you took a quarter of this box, you still wouldn't see any net large-scale effect. So now you can move on to a rotating case. This is Hughes Cattaneo. So the same problem now, but now you rotate the boundaries, sorry, rotate the system. And if the Rayleigh number is large enough, dynamo action is still possible, but there's still no sign of large-scale features. So here you see, this is the vorticity field, I believe, in the flow. And if there was no rotation, there would be no net vorticity. So because the system is rotating, this is near the top of the layer, you can see this different colours of vorticity, different signs. You see white and black tend to be the same. There is net vorticity in the flow due to rotation. But here's the magnetic field. Looks very much like the previous picture. And really the only difference between this simulation and the previous one is that the cells become a little narrow due to the effects of rotation. But nonetheless, there's still no significant mean field in the simulation or in the small scale, especially in the surface, as you see.
Mike, I mean, isn't this just dividing those two numbers? Is this all roughly numbers of a few, though, right? I mean, we're not talking about something really whoppingly.
Well, yes. Well, here's the question. So if I fix the Rayleigh number and I increase the Taylor number, convection goes away.
Yeah, right.
But then I have to increase the Rayleigh number hugely.
Right.
So at some point.
No, I'm just saying. I mean, if you take some, points regarding relative coil, so Rayleigh number divided by Taylor number.
Yes.
Somewhere like that.
Yes.
I mean, I would expect that to be, qualitatively, if that number is less than one, or
You might expect to be.
I mean, I don't know.
Well, I think there is a trade-off here. I mean, you can. The point is, if you were to, here's an amazing thing. You reduce the Rayleigh number. Sometimes you can increase the alpha rate. The more coherent flows. So it's a difficult trade-off. Yes, in an ideal world, you have very, very rapid rotation, enormous Rayleigh numbers. This is the Keith-Julian problem. And but then you have, unfortunately, the dynamo action that results doesn't feel the rotation anymore when it's too rapid, strangely. And so it's a rather subtle business. So I can't answer that in detail, actually. I don't know. But yes, of course. But the effects of rotation are significant here, and they're not negligible.
But the key point, though, is that you can have Rayleigh over Rayleigh critical, very, very large, and have Rossby, which is very, very low.
You can. Well, yeah, that's right.
You fix the criticality.
Yeah, we're looking at Rayleigh numbers which are a order one multiple of onset Rayleigh numbers. Of course, other things can happen. The larger the Rayleigh number gets, the less the rotation matters for you. Okay, so now here's the problem. The Rayleigh number is large enough for dynamo action. Dynamo is a small scale type, let us say that. But you can calculate the helicity in the flow when you have rotation. When you have rotation, you have lots of helicities, lots of correlation. The correlation between velocity and vorticity. So when it's going up, it's going around one way. It's going down, it's going around the other way, and in any particular height. And so there is a correlation between the velocity and the vorticity, which is very well developed and easy to plot. So this picture shows that the helicity, which is u dot curl u, divided by a normalization factor, so the maximum will be 1, or -1, in the layer, at the bottom and the top. So it's odd, as you would expect, about the midpoint of the layer, because of the Boost-Ness symmetry, and you can see that, depending on the Rayleigh number, things change, but here is a very well developed and smooth average that you can construct very easily over a relatively short time of the helicity. Now, if you believe that large-scale dynamos are possible in such flows, then you can experiment. Now we have to change the boundary condition a bit. Horizontal magnetic fields at the top and bottom boundaries. Get the same sort of thing with a small-scale dynamo. Now you impose a field in the horizontal direction, a uniform field. You put it onto this flow, and then you measure the EMF, curl of U cross B, average over the layer. You can measure it as a function of Z, or you can average over half the layer. If you average over the whole layer, you get 0, because it's symmetry. If you average over half the layer, you might expect to get something which is proportional to the helicity. That's what the theory says, what it's claimed to say. Alpha effect depends on the helicity. Helicity depends on the rotation. This is what you get instead. These are running totals, as it were, of the EMF into three components, X, Y, and Z. The field is in the Y direction, but you can't detect any particular EMF along the Y field, which is the imposed field, with as much of it orthogonal as there is imposed. And this average is very, very small. Even if you did a cumulative average, you still get something very small. If you go for long enough, of course, you can pin down the long-term average of this because the fluctuations are bounded. But the fluctuations are enormous compared to the mean over any sensible time scale. So what are we to make of this? There's no correlation. The problem is that there is no correlation in the production of EMF between different parts of the flow at different times. Whereas the direct correlation between vorticity and velocity, directly mediated through the Coriolis force, is much more powerful. So just to give a simple picture, it's a very famous picture from Motlet's book on dynamo theory. Why does the EMF not work? Well, it works, our naive understanding says, if the motions are helical, which leads to twisting a magnetic field line. So here's an example. Here's an upward motion which is helical. Field line, initially horizontal field line, is lifted and twisted. This leads to a current which is anti-parallel to the magnetic field. If the twist is exactly pi by 2, it's exactly anti-parallel. So, but the question is, what is the direction of this net current? There may be more twists than that, maybe two twists, in which case the current is parallel to the magnetic field. And in between, there are all kinds of other possibilities with orthogonal currents at an angle. So you're adding up, essentially you've got a sort of random set of angles which you're adding up for all different cellular parts of the flow, with wide variations. This hasn't been looked into quantitatively, but it seems very clear intuitively that the average of these currents will be rather small. Unless the magnetic Reynolds number is very small and the deviations of the field from the mean are very small, because then it doesn't go very far and it's always in the same sense. The twist is always the same, and then they can add up. Or if you have very coherent flows, which are steady, for example, and cellular, then all the twists will add up. Whatever the direction is, they'll all be the same, and so you get a coherent answer in that case. So you can take these simulations from the how do I get rid of that? I don't know. I didn't do it. I did. You can find simulations like this, and then which are very disordered, and then you solve the problem in a smaller box where the motions are perforce much more coherent because they're limited by the geometry, and lo and behold, you get a perfectly good alpha effect. So the system breaks down to large boxes because there's no horizontal correlation. So it's very difficult to see that. That all makes perfect physical sense, unfortunately. So the question is, if we impose a coherent shear flow on the basic small-scale flow that we get from the convection, does it improve matters? Certainly, we might expect to get dynamo action perhaps by some alpha omega effect, but we might also be able to make the alpha effect itself better by making everything more coherent. So here's the more recent work. We added some shear. So the question is, can a coherent shear flow lead to a change in the nature of the dynamo in these layer problems? And so just as before, it's the same problem, boost-nest convection, rotating layer with some aspect ratio, about 5 in most of the calculations, 5 times as wide as tall. But now you have an imposed sinusoidal shear, which is just added to the flow. There's some imposed u0 before you start, then you turn on the convection. So now you have convection and shear, and then you go through the same program of trying to see whether you have dynamo action and what the alpha effect looks like as a result. So now so here are the parameters. The aspect ratio is 5, the Rayleigh number is 150,000, what this is worth, and various other parameters. So it's moderately rotating and moderately convecting, but this is not a dynamo. It's a perfectly good convection problem, lots of motion, but without the shear, it's not a dynamo for these parameters. So if you put in a magnetic field, you would definitely get a decay of the small scale field. So what you can do then is add a uniform magnetic field to the system, which is not a dynamo, and what will happen is, in principle, an EMF will be produced, which is proportional to the added field. And that added field is small, and you could say that that is proportional then to the alpha effect, because the alpha effect is just the EMF divided by the imposed field. So that's the program. And so we define a shear parameter, which is the sort of typical size of the shear relative to whatever else is going on. So L is the scale of the small scale motion, depth of the layer. U0 is the size of U, and RMS is the velocity of the convection that was there before. So it's a rough thing, but we call S U0 over 300. And so when you see a shear parameter, it's defined in this way. And then for these equations, f of y is just cos y. So when you non-dimensionalize y, you just take f of y to cos y. The shear is in the x direction, depends on y. And then you have this equation, which now is non-linear, but the row this time. And you have these extra terms involving the shear, which are just added to the equations that you had before. Otherwise, all the equations are exactly the same. Here are the extra terms of the shear, the temperature and magnetic field, and 2 here and the velocity. So these are the systems that we solve. When S is 0, it's back to the previous rotating problem. And this is what you get when you add the shear. So the shear seems to make this into a dynamo. If S is large enough, what was previously not a dynamo, so here looking at the growth rate, the magnetic energy as a function of time, this is for no shear, and clearly it decays away. It's not a dynamo. So if you go on adding shear, you increase the growth rate, at least for a while, and after some threshold value for the shear, the field grows and then becomes equilibrated at larger amplitude due to the nonlinear effects of the Lorentz force. And one of the interesting things about this picture, which we don't understand at all, is that the final magnetic energy seems not to depend on the shear in any way. So there are several different results. As long as the shear is large enough, we find a threshold of magnetic energy which doesn't depend on the shear, although it probably depends on other parameters such as the ratio of the viscosity and the magnetic diffusivity we haven't investigated. But this thing where we're only varying the shear, it seems to be a universal magnetic energy system parameter. Not yet explained. So here is the growth rate as a function of the shear. Now this picture is complicated by the fact that as you add the shear, you're not changing the flow smoothly because the shear itself can lead to instabilities in the cellular pattern, as I'll show you. So we're getting these glitches down here, which is something probably to do with some sort of mode crossing. You see a sort of linear, these 3 points. As astronomers, we're all astronomers, we only need 2 points for a theory, and this has 3 points. Not a perfect straight line, and that is a linear plot, so you would agree. Theory is definite, right? Those 3 points definitely lie in a straight line. So certainly the growth rate is linear with the shear. These two are a bit of a problem, but what is happening here is that the flow has a change in its nature and becomes less effective as a dynamo. So you should ignore those and only take the points that you want. Where have we heard this before? Eh? But no, I'll show you. Okay, so this is what the flow looks like for a relatively small shear, where you can see the shear is sinusoidal, so the top and the bottom, this is the y direction. The top and the bottom, as you see, are different, and the vorticity changes dramatically in 2 parts of the layer. In one place, the shear adds vorticity, in the other place, it takes it away. And here you see the current in the dynamo working is almost all on one side. Whereas when the shear becomes rather large, you get this gyre forming. It's all periodic boundary conditions in X and Y. This is a completely different sort of flow. It's clearly some hydrodynamic instability going on here. And this changes the nature of the dynamo process as you do stuff. So this is not comparable to that. And this is a discontinuous change as you increase the shear. So you concentrate on smaller values. So there is an omega effect going on here. And the question is well, there's one possibility is that you have an alpha omega dynamo. Alpha is tiny, but omega is big enough that the product is significant and you get a mean field dynamo. Well, possibly.
How large is scale compared to the diffusion rate? And how large?
Actually, it must be about the same order because look at these pictures. You see a change in what? So yes, it's noticed. So d u naught by dz, it can't be so different, right? I can't remember. Okay, so several possibilities. So why is this working better than it did without the shear? So the large spatial scale of the shear leads to enhanced alpha effect, perhaps, through greater spatial correlation to small scale motion. That's a possibility. So just the fact that you have a different sort of flow means everything is more coherent. So alpha gets bigger, and that makes things work better. So even though alpha remains small, it may nonetheless be an alpha omega dynamo when the shear is significant. Or the shear produces anisotropy, and this leads to a more complicated to explain shear current effect, which is a mean field dynamo process which is produced by anisotropic turbulent magnetic diffusivity. It's more complicated to explain, I won't do so. So it's different from the alpha effect. It works when there is no alpha effect. Essentially, it looks at the anisotropic elements, the turbulent diffusivity tensor. You can get dynamo action together with the shear. Or, what they help to do, if you have temporal fluctuations in alpha, which you certainly do, as you saw in the original picture, even though that's not changed, the interaction of those temporal fluctuations with shear, both locally, in changing the velocity of it, and change the magnetic field, the combination, and also globally producing differential rotation. The two things together can produce an effective field dynamo. So there are these four possibilities for how the shear is enhancing dynamo. But you have to ask the question in the back of my mind, is always rather worrying. Of course, it is now an inhomogeneous problem that the shear is inhomogeneous. Do we really know what a mean field dynamo is? Well, we just have to say, is there any mean field structure to the magnetic field? Well, there is, but the only scale available really to see that large scale structure is the scale of the shear. So it may be that we're not seeing anything different, which really is a large small scale dynamo with inhomogeneity, and it wouldn't work on scales larger than the shear. This is not yet known. But nonetheless, you can get some large scale features when you have large scale shear. And it is easy to see. I can't see it myself. This says, these are power spectra in the magnetic field. In both sort of kinematic and dynamo regimes. Okay, so each one has, which one is which? Okay, they're dashed. So we're looking at the magnetic field due to the dynamo. This is when the field is very small, and this is when it's becoming equilibrated and stopped growing due to non-linear effect. And the first case, I'm sorry to read off that, because I'm not reading on there, it's too small for me. In the first case, you have some shear, and the second case, you don't have any shear. And you can see that there's more of the spectrum on the left-hand side, a small wave numbers, in the presence of shear, whereas without the shear, it's definitely a dynamo only on these relatively small scales, large wave numbers, and much less at the larger scale. And also, we can look at the alpha effect in the direction of the opposed magnetic field in just the same way. And this is the one without shear that we saw before. And you can see the noise signal ratio is enormous. And then we do the same thing with the shear, and it's just the same. So what is certainly not the case is that the shear does not help you produce a bigger alpha effect. So we're still a bit in the dark about how this dynamo is made to work better. There's no evidence of greater coherence due to the shear. Now suppose we said the growth rate was sort of proportional to S, its shear, and then presumably ignoring diffusion. So this suggests that this particular dependence on the shear may be due to the shear current effect, which has the effect of reducing growth rates, depending on the shear, they're more or less linear away, if you look at the simple models, or the incoherent dynamo due to the fluctuations in alpha and binding rotation. Both of these lead to the same growth rate model and do suggest growth rates proportional to the shear strength. If we take an alpha omega dynamo, a mean field dynamo, this is misprint here, this should say S to the half here. So this is the growth rate of a mean field dynamo with shear S and alpha effect alpha. And for a given wave number of disturbance, the longest scale of disturbances, you can see that sigma appears to go over the square root of S, and this is not observed. On the other hand, if you say that K, the wave number, goes like S to the minus a half, S to the half. That doesn't work, does it? There's no way of making S go like sigma go like S, except by having very peculiar scalings for the scale of the disturbance. So one has to conclude that this is probably not, at least the first conclusions are, this is probably not a mean field dynamo of the traditional alpha omega kind, even though you might think that it would work that way. Scaling is just don't seem to be right. So then we did something else, trying to at least decide what was going on. So to decide what properties we wanted contributed to the dynamo, we looked at filtered flows. We've only looked so far at kinematic problems, so that the magnetic field does not affect the velocity. We start with the velocity field. We solve the non-magnetic convection problem at high resolution. We do the full problem, do it correctly. Then we take the velocity field, which comes out of this, and we filter it in real time. We cut out certain parts of the spectrum. So now we have a velocity field which does not have a complete spectrum. And then we solve the induction equation in real time using the filtered velocity field at high resolution. So the magnetic field is fully resolved, and the velocity field is played about with. But can play about with at every time step to get rid of certain Fourier lines. So this is not a low pass filter solution of the induction equation. The induction equation is solved properly with the maximum possible resolution. And so is the convection problem, where we just take bits of the correct convection problem and take bits of it away in order to see what it does to the magnetic field. So we do two kinds of filtration. The first one, we get rid of all the some small scales. So we cut out the smallest scales, the largest wave numbers, gives you a smoother flow, but the large scales are left intact, the same large scales as the real flow. Or we retain the shear, and then we produce a separation of scales by removing modes with wave numbers sufficiently small, except for the shear. With the shear and then small scale stuff with a gap between them. So if the system were a mean field dynamo, you'd think this would tell us the answer when we get the right sort of growth by looking at the scale separation. Whereas if it's something else, then this would give me the right answer. So if I was being annoying, I would ask you to decide what would happen to the growth rates when you did this filtration. But because the answer is so surprising, I'm not going to ask you. So here are some examples of filtered flows. So this is for a given shear, S is 5/3. So this is a dynamo when we don't filter the flow at all. So this is the vertical velocity, contours, and this is the residual for filtering, and only K is the residual. This is a filtered flow with K less than 30 retained. So K is some composite wave number made up of the horizontal wave numbers. And what's left is this very small scale stuff that you see here. So this plus this is the actual flow. This is not so different from the actual flow. And here's the effect of doing three similar filtrations, K less than 30, that's that one, K less than 10, K less than 5. So all we have here is K less than 5, and the structure of the flow has started to change here. Whereas this is still a fairly faithful model of the whole flow, but it doesn't have any scales that are too small. Okay. So let's look at some magnetic spectra for truncated flow. So now we've solved the induction equation, we can look at the spectra. So the shear is retained, and again, this is the wave number down here, and this is the magnetic energy spectrum. This is what we've got. So we've kept the shear, and we've made a gap in the spectrum. But the large K part of the spectrum doesn't look very different. The small K part of the spectrum is changing because now there is a separation of scales in the flow. But nonetheless, there's still plenty of large scale, not just the shear, some other stuff as well in the intervening region. I just want to emphasize that in the flow, there are no wave numbers less than 10 apart from the shear itself. Here's the opposite situation where large wave numbers are removed and everything at small wave numbers is retained. And you can see that this particular problem, different truncations, you can now call it, in wave number space don't really change anything where the energy is biggest. Down here there are some changes because the flow is smoother when it's more filtered. Essentially not very much difference there. So these are very different because of a different way we've organized the flows. So you'd expect different growth rates. Well, here we have 5 different high wave number truncations. So the mode's retained, so this is essentially untruncated, k less than 40, and as you go up, it's more and more truncated, the flow becomes smoother and smoother, and by the time you get to k is 5, you've really lost all the small scale flow, except the very smoothest parts of it, and you might think by now that you can see some effect on the dynamo growth rate, which you don't. We leave out A. I mean, the first thing to notice is that these growth rates are not monotonic. What you do see here is for the bigger truncations, the system takes longer to get into a sort of final state where it's growing more or less exponentially. But once it started to grow exponentially, these growth rates are all comparable. This one is a bit bigger than the others. All the rest are much the same, and they don't go monotonically with filtration. So, as fast as Cattaneo would say, go figure. I don't understand this. I present this to you as a simple fact.
Find the magnetic spectra that you showed us, those were all kinematic.
Everything is kinematic. Yeah, we haven't done the next bit. Because that would alter the flow. We want to tightly control the structure of the flow. So those are high wave number truncation doesn't seem to do anything. So that suggests that it's not a dynamo that depends on the small scales. It must be a mean field dynamo. It's not obvious, but there's something odd here, because what we thought we had was a small scale dynamo, but actually it turns out it only depends on the intermediate scales, in fact on quite large scales. And then we do this. So now we have 2 completely different sorts of filtration. We remove the modes retained are k greater than 5 and shear. So now we have essentially we have a small scale flows, but we have a big scale separation. And we have, here's one now with the small wavelengths removed, and the growth rates are essentially the same. So what we thought, well, the previous, we thought, well, everything depends on k less than 5, because even when we only have k less than 5, we get the same growth rate. And then we go to the next one, and we get rid of k less than 5, apart from the shear, we get the same growth rate with essentially uncausal problem. Well, maybe it's not so surprising. But the point is that it's very difficult to get any growth rate other than this growth rate. The different things you do to the flow lead to the same answers all the time. So here's a conclusion, which isn't really a conclusion, it's inconclusive. And we need to do more work. So what can we say? If you have put large-scale shear into a rotating convection problem, then of course you do produce inhomogeneities in one of the horizontal directions. And you do get large-scale features in your magnet. This is not so surprising. It isn't obvious that this is actually a mean field dynamo with field operating on scales much bigger than the convection. We want to attempt to scale that. But what it's certainly not the case is the shear flow does not make alpha better. So the mechanism is something else. You still have this very weak alpha effect, very incoherent. So it's probably not a mean field dynamo in that sense. It's something to do with the larger scales and the way that they interact. And we can just ignore the small scale in the flow. Interesting. But it's probably not a mean field dynamo. On the other hand, we could think this is a plausible characterization of a 2-scale dynamo because we've got a magnetic field, a velocity field, which is explicitly made 2-scale, and it seems to give the right answer. So these 2 statements sort of, they don't really go along with each other. And we need to do more work, basically. But it's clear that the effects of shear are complicated. We just need to do a lot more work on trying to understand just what properties of the flows report. And of course do it in a nonlinear regime if we can understand how to do that without, and as well as looking at the different scales of flow. So that's almost the end. Can I have 5 more minutes? Because I want to say something else. Postscript. And this is about another paper by Kapfer, Corpy, and Brandenburg. Some of you may have seen this paper, who claimed to solve our problem and get completely different results. Always annoying papers like that. So can we reconcile, that's the polite way of saying, can we reconcile our results with their results? Okay, so in green italic is what they claim. Okay, so the first thing what they find is that, I'll tell you the differences between the calculations. What they find, they claim that alpha effect is much larger than we say it is. And it can be understood by the so-called resetting method for calculating alpha effects in terms of close. They have a technique for working out the alpha effect. They say it's very big and compared to ours, and they can't reproduce our results. So, they say alpha and the EMF have a sinusoidal profile orthogonal to big, which is true because of the shear. And therefore, although the alpha effect may be large, it can be large locally. But in fact, this is an example here. It doesn't have a sinusoid. Actually, alpha does not have a sinusoidal profile because alpha has a well-defined mean as well as a sinusoidal part. You can see this. This is a plot of the alpha effect in their simulation as a function of the direction across the shear. You can see the right half is different from the left half as the shear increases, but when there's no shear, then the alpha effect is more or less uniform across the Y. When there's lots of shear, there's very little here, but quite a lot here. The red means 0. Didn't show the colours here. Red means 0. So the mean is scarcely affected by the shear actually. So that's not a reason for thinking that you get cancellation. And also, their calculation, it's very hard to know their parameters, but they are solving the problem much closer to the supercritical value of convection. So it's a more coherent flow. You might expect bigger alphas for reasons I've discussed. Then they say that alpha is large near the boundaries. It can't be found by looking at the EMF. There are turbulent currents. Well, the problem with their problem is that this is the crucial figure here, again from their paper. This is the imposed field. And this solid line, or one of these bottom lines, doesn't matter which one, I can't see with my 4 eyes, is the induced field in the same direction. Right? So the flux in the direction of the original field is the sum of this dotted line and one of these negative lines, i.e. almost 0, except near the boundaries. So the total flux in the system has changed. Furthermore, one of these other lines represents flux in the orthogonal or horizontal direction, which was 0 at the start of the calculation, is now non-zero. They have different boundary conditions. They have vertical field on the boundary, but an imposed horizontal field just inside is incompatible with the vertical field boundary condition. There's an inherent contradiction, and if you follow their analysis along and work out whether the flux is conserved in the horizontal directions, in their case, it's not. So this system, their system, pulls in magnetic flux, horizontal flux, from the outside of the computational domain, rather than conserving it as our work does. So, in fact, it's impossible to compare these results because of this, I would regard as a flaw in their boundary condition. They also talk about resetting. They say, the only way correctly to calculate the alpha effect is not to look at induced turbulent, mean magnetic fields. Well, that's a point of view I don't personally agree. But they say the only way to do things properly is to integrate. You start from no fluctuation field, you take the velocity field, you integrate for a finite time, you measure the alpha effect then, and then you start again. And you do this again and again and again, and you get a coherent average. And then you have to choose the so-called resetting time. So we integrated our system for a time of 0.05. So the maximum resetting time here was 0.05. So each of these lines represents a simulation of the problem for a time of 0.05, starting from 0 fluctuating field.
Is one magnetic
I think the magnetic diffusion time is around here, actually.
Oh.
I think. I'll tell you. Certainly, inductive effects are very important by the time we get to here. So what you're seeing here, yes, diffusion is operating here. Diffusion is not operating here. And what you see here is if you have very short resetting times, then you do get some coherence because the field obviously is correlated for short times. You'd expect that, right? So all of these, you get all these 90 runs, all these 90 runs give more or less a similar alpha if you stop here each time and then average good runs. If you go too far, it starts to come down again due to cancellation and reconnection effect. And if you start at 0.05, which is quite short actually, you might think compared to the time you're running the system, the average of this is 0. So the task of Capilla and his collaborators is to choose the correct resetting time. Which one do you choose? Well, not this one. You get nothing. Not this one, because you get this very short one. You get nothing here either. So which one of these and why do you choose it? So my own submission is I can't see which one you choose to get the right answer, because the answer is different depending on what you choose. And so I can't see that this method can actually ever tell you what the alpha effect ought to be. The only way to do it is to get to a statistically steady state, it's anything that makes sense, and then measure the statistically steady EMF, and then call that the alpha effect times the imposing of that's the only thing that seems to make sense. Because if you take these averages for long enough, you do get an answer, it's almost zero. But in other problems, you might get something that was non-zero, and then that would be the right way of working it out. So I feel that for several reasons, this paper, which seeks to suggest that there are bigger alphas than we found, is not solving the same problem. And alpha effects are being calculated in a way which I don't understand. So I'll better leave it at that. Thank you very much.
So we're good over.
Sorry.
But if anybody needs to leave, go ahead. And if you have any questions, make a couple, and then we can cook it, of course. Maybe afterwards. Anybody?
Yeah, sure.
If I could just rephrase my question about the small-scale convective dynamo.
Yes.
The extent to which it depends on magnetic Reynolds number. If one takes magnetic Reynolds number to be enormous, 10 to the 20,
then inevitably, in my view, inevitably, there will be small-scale dynamos everywhere, all the time.
on the scale of
On the scale of the convection. So then you have to ask, does any of this have any meaning? Because then in this case you have to go to a completely different scenario where you have an MHD state on the small scale. Now there are inhomogeneities acting, so that may be the source of large-scale fields, which may be relatively weak. Or there may be some instability process which yields long-scale modulation of this, initially, say, in some model, homogeneous MHD state. So actually this is something that Hughes and I have been working on. And you have to replace the simple mean field induction equation, which is linear, with a couple pair of equations for mean fields and mean flows. We don't know how to calculate coefficients, except in very simple cases. But you can see that the proper thing to do is to solve this coupled set of equations, which will yield completely different answers from this. I absolutely agree with you. I mean, we're following a path others say is important, but it's my view that kinematic dynamo calculations with the large magnetic Reynolds number in the small scale is not going to be useful in understanding astrophysical flows. Is what you were trying to say.
I mean, some of the turbulence in the box calculations, for example, I think Cowley's group
Yes, they do a lot.
give more ambiguous results. That way you would build up the magnetic power spectrum to the larger scale.
Yes, so it depends.
And so why then is the convection potentially different from unstratified turbulence?
Well, it has, of course it has, only because it has up-down inhomogeneity, of course. I mean, there's less homogeneity. And I think these calculations that use isotropic forcing are very interesting indeed, but they start from a different point of view. And they're no doubt applicable to parts of the interstellar medium and so on, which is where they're very interesting. And the whole thing does depend on the magnetic Prandtl number as well. A lot of the Cowley calculations have a very large mu, very small eta, completely different limits than one we want to understand. No, I have no objection to those problems. I'm just trying to get closer to what is actually happening in the sun. This one is doing a convection problem. It doesn't look like solar convection, but we're sort of beginning to get into the correct ballpark with the anomalous simulations.
I think with that, we'll take it upstairs for snacks. Thank you again.